Hi guys, in this video we're going to continue working on chapter 2 and kind of building up some of the key assumptions and principles happening within statistical mechanics. So just like the previous, this also comes out of section 2.2 in your textbook, and we are building up some terms and definitions that we're going to use for this entire section of statistical mechanics. That's why I'm making sure to spend a decent amount of time on this. Okay, so statistical mechanics is using probability theory or statistics to describe the properties of macroscopic groups of molecules. Remember in the last video we were talking about how one molecule of benzene behaves differently than a container, a beaker, hopefully not a beaker, a flask with a sample of benzene. And so the properties between these are different. And statistical mechanics is going to work to use statistics to determine these properties based upon the properties of the individual molecule. And why this works and why we can do this is based on some of the key assumptions that we are going to make. Okay, now, think about assumptions. Many of these assumptions that we're going to talk about will seem very obvious. Physical chemists, we hate making assumptions. We don't want to do it. And when we do, we make sure to put those assumptions into words, because what it allows us to do is to understand that when something isn't behaving according to our model or our prediction, that it's most likely due to an assumption that we are making, and we go back to those assumptions to try to figure out, well, what is missing? Okay, so our key assumptions that we are going to make this semester. Chemically identical molecules share the same physics. Okay, so back to our molecule of benzene versus our closed flask of benzene. It is an assumption to make that this molecule 1 here by itself, behaves the same as molecule, we're just going to call it N, in this flask. And so if I have a beaker of water, we are going to assume that every water molecule behaves the same. Now, this seems self-evident and obvious, but this is an assumption that we are making. We also make the assumption that macroscopic variables, this should be variables, are continuous variables. So while parameters such as energy are quantized within individual molecules. So remember how we said that our electronic for our benzene molecule can only have certain energies? This is true for that individual molecule. But when we consider the bulk or a large sample, the quantization disappears and any value is possible. So it's continuous. And so the energy of the sample is no longer quantized. We are also going to assume that measured properties reflect the ensemble average. Okay, and we're going to talk more about what the ensemble average means in a little bit, but for now, let's just go with this definition. if we fix some of the parameters, so we set some of the parameters as known values. So, for example, the volume and number of molecules. We can imagine that the very large set of all quantum states that of the system can correspond to some average or overall measurement of the quantum states. Okay, so this last one is an assumption, and we're going to really dive in and expand upon this one. We're going to focus in on this last one. Okay, so let's get some more vocab under our belt. The ensemble. The ensemble is a large collection of molecules, and large can actually be pretty small. But remember, we talked in the last video that if we can see our sample, that is so much larger than individual molecules that we are into the bulk. And so this ensemble is when we have the bulk. And the ensemble is another word for the system that we are studying. So this large collection of molecules, remember, each have their own properties governed by quantum mechanics. But we are going to be looking at what the bulk properties happen to be, which are some combination of those individual properties. Ensemble size, which we define with the symbol omega, this is the large number corresponding to the number of individual configurations of molecules in the ensemble. So we're going to talk more about this in a minute, but it's a number. It's the number of different ways that the ensemble can orient itself. A microstate is a single unique configuration of a species within the ensemble, and the ensemble average is the property of the bulk that is observed. Okay, let's talk microstates a little bit more. If I have 3 pairs of shoes, I have 2 sneakers, which I have given red dots, and I have 1 set of heels. I know I have more than this, but let's just simplify my shoe closet for a minute. And I have a shoe organizer, a cubby. I have options of how I can arrange the shoes. I can do my sneakers on this side and then my heels on the bottom, or I could do the sneakers on this side or my heels on top. And if I start moving things around, I end up with 12 different arrangements of my shoes in my cubby. And what this is that each arrangement is a microstate. And the whole collection of the arrangements is the ensemble. And in this case, omega, our number of microstates, is 12. Okay, so that's shoes. Let's think about this in terms of molecules. So if we think that about energy, and so a microstate can be a particular arrangement or state that a molecule can exist in. So particular energy, so translational, rotational, vibrational, electronic. The ensemble is a large enough collection of molecules that all possibilities of arrangements or configurations exist. And then this assumption that all microstates exist within an ensemble is known as the ergonic hypothesis. So, as we think through the number of possible microstates in a molecular system, you might be thinking, oh my goodness, this is huge. How in the world can we deal with this? Because the example that I gave was just thinking about the quantized energy levels. There are a lot of variables happening within our flask of water or benzene or whatever molecule that we happen to be looking at. There's energy, pressure, volume, temperature, number of molecules, and many other things. And starting to think about how to isolate one of these variables as the rest can be changing or unknown starts becoming a challenge. So ultimately the macrocanonicle, or sometimes known as the grand canonical ensemble, this is the real answer. It allows all variables to change within a system. We're not going to attempt this. This is graduate level statistical mechanics. Feel free to take that course. I did. It was challenging. But what we're going to really focus on is the microcanonical ensemble. And in this, all extensive properties, energy, volume, remember these are the properties that add, will be held constant. So we're going to have a known energy. We're going to have a known volume. We're going to have a known number of molecules, or a chosen. And these are going to stay constant. And then all intensive properties that are ratios of extensive properties, like density, that is density equals mass over volume, both of these are both extensive. And so if all of my extensive properties are constant, then density, an intensive property, is also constant. Now, if your brain's anything like my brain, you're probably going, hold on, are there any properties left? Turns out that yes, there are. We will be able to determine all microscopic parameters that we don't measure using thermodynamics. So like energies and positions of individual molecules. So this is more of the quantum world, the quantum mechanical world. And we can look at intensive properties that are not ratios. So things like pressure. So the following parameters are always constant: energy, mass, number of molecules. And all parameters in the microcanonical ensemble are intensive properties or an average value of the microstates in the ensemble. Okay, so now try this. A system includes 2 particles occupying 4 microstates. What is the value of omega, or the number of microstates for this system? So for this, we are talking kind of like my shoe cubby example. I have 4 possible places for these 2 particles. And I'm asking you to think of counting the number of arrangements for this system. Okay. Stay tuned. We're going to move on to section 2.3 in the next video.